For the next videos, it's still Math 1325, Chapter 12.4. I think this is video 4, right? So similar to the last section, we're going to sketch the curve. Last time we did polynomial, and this time we did rational function, so it's a little bit more complex. So this one we need to find the domain, intercept, asymptotes, decide what the end behavior is. And remember, when we want to find increasing, decreasing, and the relative extremer, we do the first derivative. When you want to see the concavity and inflection point, you do the second derivative. Sometimes you may need to plot additional points for the graph, and it's a pretty complex question, so we're going to try to do this together. So you probably need a piece of paper because it's going to be lengthy. We're going to sketch this function. They want a lot of stuff. They want to get the domain, intercept, interval that represent increasing, decreasing, and then concave up, concave down. So increasing, decreasing is first derivative. Concave up, concave down is second derivative. Local extremer is first derivative. Inflection point is second derivative. All right, let's see. I got a piece of paper, and I'm gonna get started. So this started with the question say the rational function is f of x equal to x plus 1, x minus 1. So it looks like something as simple as we can make it together. The first question asks for domain. So remember, domain say when you have a rational function, basically the bottom part, denominator, cannot equal to 0, right? So if we set denominator cannot equal to 0, that would be x minus 1 cannot equal to 0, so x cannot equal to 1. So my domain should be starting from negative infinity to 1, skip 1, pick up 1 to infinity. Or you can say all real number except 1, right? The next part they ask for intercept. So we have x-intercept, and then we have y-intercept. For x-intercept, we need to set y equal to 0. For y-intercept, we set x equal to 0. So let's see, if y equal to 0, like this, then I need to get rid of the denominator, right? By multiplying denominator to both sides. So this got canceled out. On the left hand side is going to be 0 equal to x plus 1. So you can think of it as a fraction equal to 0. Basically mean the top part of the fraction is equal to 0. Solve for that, x equal to negative 1. So my x-intercept is going to be negative 1 for x, y equal to 0, right? For y-intercepts, I'm going to set x equal to 0, so y equal to 0 plus 1 over 0 minus 1, y equal to 1 over negative 1 is just negative 1, right? So for my y-intercept, I have x is 0, y is negative 1. Alright, so far everybody's okay. The next part they asked for, they didn't ask for asymptote, but we probably need it. Maybe they forgot. So let's go ahead and find asymptote. So we have vertical asymptote, we have horizontal asymptote. I don't have slant asymptotes, and asymptote has to be the top part is exactly 1 degree higher than the bottom. So how do we find vertical asymptote? We basically set denominator equal to 0. So x minus 1 equal to 0, x equal to 1. So make sure you write x equal to because it's a vertical line. Horizontal asymptote, we just need to have y equal to the leading coefficient on top and then the leading coefficient at the bottom, right? So we have y equal to 1x and 1x. So basically, the horizontal asymptote is just y equal to 1. Alright, so we found those. What's next? We talk about intercept. I need to know the interval of increasing, decreasing, and concave up and concave down. So if you want to find increasing and decreasing, you will go with the first derivative. So f prime of x. You can do a quotient rule, you can do product rule if you make this a negative 1 as the denominator. So I'm going to just go ahead and practice my quotient rule. So remember first, we need to write the bottom part with square. Then you start with which one? The bottom guy, and then the derivative of the top guy. And subtract. Subtracting the bottom guy, take the derivative of the top. Alright, so that will end up with x minus 1. This take the derivative with just 1 minus x minus 1. Sorry about that. This means x minus 1. Take the derivative of that is just 1. Alright, bottom part is x minus 1 squared. So I'm going to end up with x minus 1. So I have to be careful with this negative sign. Minus x plus 1, right? And then x minus 1 perfect square. And after reducing something, 1 is gone. I'm sorry, 1 is not gone. Hold on. X, I copied it wrong here. X plus 1. Sorry about that. So this would be a minus here. So sorry, I made a little mistake here. So I copied wrong. This is supposed to be the top part. Take the derivative of the second part, right? So please help me to correct that. So that was positive here. That was because it was the bottom part, and then take the derivative of the top minus the top part, take the derivative of the bottom. So that's supposed to be minus. Oh, sorry about that. I'm gonna make you so confused. X minus 1. Okay, let's start one more time. So the original question, f of x, was x plus 1, x minus 1, right? So when I apply the quotient rule, it's going to be the bottom square. Start with the bottom part, x minus 1, take the derivative of the top. Subtracting the derivative, the top part, take the derivative of the bottom. So they kind of swap, right? So I didn't do that earlier, sorry about that. So this is x minus 1 minus x, and then this would be minus 1. So hopefully everybody got it corrected. So this one will not go away because it's minus 1 and minus 1, but the x minus x go away, right? So this will give me a negative 2 on top, and then I have an x minus 1 at the bottom square. Alright, so this is my f prime of x equal to negative 2 x minus 1 squared. I should have done the product rule. If we write that into the product rule, I probably will not make that mistake. Sorry about that. So hopefully this is clear now. If not, if you have questions, please email me. Using that, if we set the top part and the bottom part equal to 0, we can find a critical number. So for the rational function, we're going to set top equal to 0, which is negative 2 cannot equal to 0, and then set bottom part equal to 0, which is x minus 1 times x minus 1 equal to 0, x equal to 1, x equal to 1. So x equal to 1 is the critical number. And then remember we set a table, x equal to 1, So this is negative infinity to 1, and then 1 to infinity, and we test applying of a number. So test x equal to 0, x equal to 2 maybe. So applying of 0, applying of 2, because I want to see if the first derivative plug in that number is positive, that's increasing, negative is decreasing, right? Plug in a 0 for what we just found here will give us a 0 here, negative 0. That's going to be a negative number, right? So if I have a negative number, then the function will be decreasing. If I plug in a 2 here, I will end up with another negative number. So applying of x equal to negative, it means the function again is going to be decreasing. So I can say that it's going to be increasing is none, decreasing is going to be all the way normally, but remember x cannot equal to 1 is my domain. X cannot equal to 1 is my domain, so at this point it does not exist, right? So when because if x equal to 1, it will make the bottom part equal to 0, right? So decreasing would be negative infinity to 1, but I have to skip 1, go to positive infinity. So decreasing is negative infinity to 1 union 1 to infinity, because this is a rational function. So it skipped the vertical asymptote. All right. So because it's going down and down, so going down and down some more, so I don't have any local extrema, right? Or relative extrema. Okay, so that's one part of the questions. And the second part of the question is asking about the concavity. So for the concavitive change, we need the second derivative. So first derivative, say that negative 2 here, and then x minus 1 squared, right? So if I take one more time, let's see. For the second derivative, let me try one more time with the quotient rule and see if I will do better. So the bottom part need to be square. It's already square, so you square them. And then I start with the bottom guy. Take the derivative of the top guy. So slow down and think about it. And then the top guy, take the derivative of the bottom one. That's not good, because that's going to be my chain, right? Okay, like that. Okay, so let's see. If I have that, the bottom part is simple. It's just 2 times 2 is 4 power. The top part, if you take the derivative of a number, you will end up with a 0. So that makes things better. Let's see, sorry. That's the 0. And then negative times negative become positive, I guess. Positive 2. Taking the derivative of this guy, I have to be careful. That's a chain rule. Put down the 2, x minus 1, go 1 down for the exponents. And then take the derivative of the inside part, right? X minus 1. So this times 0 becomes 0 plus 2. This is 2x minus 1. When you take the derivative of that, this end up with 1, right? So what do I end up with? I have 2 times 2 is a 4. X minus 1, x minus 1 to the 4th power. It looks like I can reduce, right? So I can reduce one of this, and then this becomes 3. So f double prime of x will be 4 on top, x minus 1 to the 3rd power at the bottom. So this is the second derivative. Once I have the second derivative, I can check the concavity, right? If the second derivative come up positive people look like smiling, so concave up. If second derivative plug-in number equal to negative, then negative people is sad, so it's a frowny face, concave down, concavity. So set the table here, supposed to be set top equal to 0, bottom equal to 0. So 4 cannot equal to 0, x minus 1 to the third power equal to 0, x equal to 1, but remember 1 will make the denominator equal to 0. So even though you put x minus equal to 1 here, this point does not exist, right? So I want to remind myself that. So this is negative infinitive to 1 and 1 to infinitive, right? I need to check second derivative. This can plug in a 0, this can plug in a 2, right? If I plug into my second derivative, this one will end up with a negative, this one will end up with a positive. What does that mean? So negative people is usually sad, right? Positive people is usually happy, right? So this is concave down like a frowny face, this is concave up like a smiley face. So because I change concavity, normally this is inflection point, right? But because this point does not exist, so no inflection point. Okay, so concave up is 1 to infinitive, concave down is negative infinitive to 1. X equal to 1 does not exist, right? Because it makes the denominator equal to 0. So x cannot equal to 1. Because of that, no inflection point. Even though this is changing concavity because that point does not exist, so no inflection point. And earlier, we already found the intercept is negative 1, 0, 0, negative 1. Is that what we found? Okay, and then we also found vertical asymptote is x equal to 1, horizontal asymptote is y equal to 1 also, and let's see, we also have decreasing is negative infinitive to 1 and then 1 to infinitive. So I think, did they ask us to graph this? Oh yeah, they say sketch the graph. Okay, so we're gonna need to graph this. So on the graph, I can put my asymptotes. So I have x equal to 1. I have y equal to 1. So it set it up into two sections with the vertical asymptote, so two pieces of graph. And then I have some intercepts. So intercepts say x equal to negative 1, 0, y equal to 0, negative 1. So right here. So it looks like it's going to be a curve like that because the graph is supposed to get close to asymptote. It's either this curve or the top curve. And because I have to go through these two intercept points, so it's down here. So the other one, you can either test the point here, or I know it's going to be here, y. Because I have one x-intercept, I already caused that, so this side I don't have any x-intercepts here. So I know it's on top. How about the concavity? Is that correct? Let's see. Concave up is here. Looks good. Concave down is negative infinitive to 1. It's like here. So that's good. So it looks like it fit all the information. So that should work.